Welcome to the course on two-dimensional signal processing, principles and practices. We are doing the Z transform in 2D. So the examples we continue with few more. The thing is x of n1 comma n2. Suppose we take the sequence of 2D is a power n1 ut n1. So this is a sequence. T can be of 2D as well. Here it is representing this 2D n1, in which this n1 greater than or equal to 0, this sequence will be 1. So we take this ut of n1 as the sequence where n1 greater than or equal to 0, and n2 can be of both the values, that is negative and positive. So here is that. So the sequence would be in this way, it would continue from here to here, n2 minus infinity to plus infinity, or where n1 is from 0 to infinity. And this sequence is multiplied by a of n1. So a n1 is having n1 0, this would result in 1, and n2 is 0 in all the cases. So we have this sequence will have all the values 1 1 1, and here is 1, a of n1 is 1, so this gives a and a square and a cube. So this is the sequence now. So what is the Z transform of this sequence? It is depending on only n1, the function of n1. So we can easily find the ROC and the Z transform of this sequence, whereas x of z1 comma z2, n1 is varying from 0 to infinity as the sequence is in the right hand side of that, and n2 take minus infinity to plus infinity, both the values. So this is a of n1. So this is restricting the first summation to 0 to infinity. So the second summation is from minus infinity to plus infinity, so because n2 varying in both the directions. So a of n1 is z power minus n1 and n2. So we can have this check whether this can converge or not. Okay, so if you write this, a is z power n1 of minus 1 or n1 and z2 minus n2. So this sequence, if we take the n2 is varying from minus infinity to plus infinity, so this sequence doesn't converge. We could not find the closed form solution for this case. So this sequence is spreading from minus infinity to plus infinity, that doesn't have the closed form solution here. So we have this sequence will not converge. Okay, so we'll not be able to take the Z transform of that sequence. So it doesn't exist in this case. Okay, so that to be noted, because this sequence will be spreading to minus infinity to plus infinity. And if you take the other example of the one more, some peculiar cases or the specific examples of it. Okay, now if you're taking the example of the 2D impulse. So the 2D impulse, we know that n1 and n2 are 0, this is going to be 1. So the 0 indicates the position of this n1 and n2 are 0. So that in that way the impulse that is taking that unit impulse, it is 1. And for this sequence, what is the Z transform? So the unit impulse of 1D, we have it is spreading over all the Z values, right? So the ROC, so we'll see it is equal to 1 in the case of Z, in the Z plane. It has all the Z plane in the case of 1D. So let's see in the 2D case that x of z1 comma z2 is also equal to 1. You can see that n1 varying from minus infinity to plus infinity, and in the summation n2 as well. Del of n1 comma n2 exists only at n1 equal to 0 and n2 equal to 0. So when we make this 0 0 and this is 1 at only one point, so this result in, so the whole thing converges to 1. So the Z transform of the 2D impulse is 1. So Z transform of 1D impulse is also 1. So this is going to be 1, and for all z1 and z2 values. Okay. So for all z1 and z2 values, the convergence if you take, we see is that the whole region, so that is z1 z2 is going to be the whole region is the ROC. For all z1 z2 value, this would converge to 1. So because it is this x of z1 z2 independent of anything, so it's going to be 1 for all the values of z1 and z2. So it would converge to all values of z1 z2 in the z1 z2 plane. So this is represented here. And if we take some product of this impulse and the step sequences, so z2 2D N2 is the impulse. So this impulse is like a horizontal impulse. So when N2 equal to 0, that means delta of 2D N2 is equal to 1. So this is what is N2 equal to 0, this is 1, 0 otherwise. If you recall that very starting of the 2D sequences, we have done the horizontal impulse and the vertical impulse and the unit impulse of 2D and diagonal impulses also. So here is this N2, which is the horizontal impulse. So this horizontal impulse obey this equation, and the step sequence we know, that is if product of these two, a step sequence u of N1 comma N2, in which that you have this is existing for N1 and N2 greater than or equal to 0. So if you multiply these two sequences, so in this portion it is 0. So only the line which is over here would exist, it will be 1. So the sequence which the product of these two sequences is the N1 N2 having only the impulse in the horizontal for N1 greater than or equal to 0. So this is the product of two sequences. So what is the Z transform of this one? So if we take, this is going to be 1 for the values N1 varying from 0 to infinity, and this summation N2 minus infinity plus infinity is not valid. Okay, so these are all 1. So this is not going to be helpful. So this N2 is 0 for all the cases for the signal where it is existing. So this portion is becoming 1, and this is going to be 1, and we have this term in the summation N1 varying from 0 to infinity. So this is also restricted because of the sequences from 0 to infinity. So this summation, the whole summation of this product of two sequences results in a simplified form N1 varying from 0 to infinity summation is Z1 power minus 1 N1. So this one is 1 by 1 minus Z1 minus 1. What should be the ROC? So Z1 minus 1 should be less than 1. Z1 power minus 1 should be less than 1. So Z1 should be greater than 1. So for all values of Z2, so it is independent of the Z2, this x of Z1 comma Z2. So for all values of Z2, so this ROC needs to be considered. So here is it's only for all values of Z2. So in the sense Z1 greater than or equal to 1 is this line. This is 1. This line is Z1 equal to 1. Equal to 1 is this line, and greater than is this one for all values of Z2. So Z2 is can take this value. So the region ROC is existing here in this region. So for this example, that sequence of horizontal impulse which is having only right sided or the N1 components, N2 for N2 0, N1 varying from 0 to infinity, this has the region of convergence as greater than 1. So the next example where u of N1 comma N2. So we had seen this is separable, and the step sequence. Also we can use that property. Also we can see that u of N1 comma N2, if we plot, we are using it for along with other sequences. What is the Z transform of this? So we take the Z transform of this one. So this N1 and N2 are restricted at the lower side from 0 to infinity and 0 to infinity. This would become 1, Z1 minus N1 is Z2 minus N2. So here 0 to infinity. So this is Z1 per minus 1 power n. So we get it here. This value becomes 1, and Z2 power minus 1 power n. So now the closed form solution can be obtained 1 by 1 minus Z power 1 a, that is Z1 power minus 1. So which is over here, and the second one is also valid for the summation 0 to infinity 1 by Z2 power minus 1. So this is possible only when Z1 minus 1 is less than 1 and Z2 power minus 1 is less than 1. So from this Z1 is greater than 1 and Z2 is greater than 1. So we get the two ROCs. ROCs is Z1 and Z2 power minus 1 is less than 1. So Z1 is greater than 1 and Z2 is greater than 1. So Z1 equal to 1 is this line, and Z2 equal to 1 is this line. So we have Z1 greater than 1 corresponds to this portion, and Z2 greater than 1 is also corresponding to this portion as well. So all these portions. So the intersection of the two is the region of here. This is ROC here. The ROC of the step sequence, which is also a first quadrant sequence. We have seen this in the some of the examples where A is not 1 and B is not 1 and different values of A and B. Here we can use this, we have seen the examples. This is only for simply the step sequence. The sequences which are restricted with the step sequence will also have the N1 and N2 will have this ROC similar to that. If we take another example of this 2D impulse in which the 2D N1 and 2D N1 minus N2. So, you can see this is the diagonal impulse. So, 2D N1 is N1 greater than or equal to 0, this sequence will be 1. So, that we can plot it. So, N1 greater than or equal to 0, this is the step sequence which is having N2 spreading from minus infinity to plus infinity, and this is 1. So, the case of second one, if we take multiply this the diagonal impulse. So, the diagonal impulse has the slope N1 equal to N2. So, whenever this N1 equal to N2, this is present in the impulse, even the negative N1 and N2, but the other values of N1 and N2, that's going to be 0. So, it's a diagonal impulse. So, if we take the product of these two, so we would have this sequence resultant would be only at this point, 1 here. So, multiplication would result in only this sequence. So, we can see that sequence is this N1 and N2 product of that. So, what is the ROC of this sequence and the Z transform with that? Z transform will find out. The Z transform is N1 minus infinity to plus infinity. So, now this summation and the resultant one that would change, which is having N2 and N1 equal values. So, N1 varying from 0 to infinity, and this the whole thing becomes 1. So, Z bar Z is Z1 or minus N1, Z2 or minus N2, where N1 and N2 are equal. So, N1 and N2 equal, and this value is from 0 to infinity. Okay, so N1 is varying from 0 to infinity. So, it is also depending on N2. So, N1 and N2 will be equal. So, we can have this N2 is equal to 0 to infinity. So, we can have that here as well. So, N1 and N2 are equal. So, that needs to be taken care of. So, now we can simplify this. So, as Z1 power minus 1 and Z2 power minus 1 whole power N1 and N2 are equal. So, we can put N1 equal to N2. So, that is going to be N2. So, the summation now is reduces to N1 equal to 0 to infinity is this. So, this needs to be less than 1 or minus 1, Z2 minus 1 should be less than 1 for this to have the closed form solution. So, 1 by 1 minus Z power 1 minus 1 and Z2 power minus 1. So, this is the Z transform of this sequence. The diagonal impulse which has values N1 varying from 0 to infinity, not in the negative value, where N1 and N2 are equal, it has a slope. For this case, the Z transform of this. What about the ROC of it? So, ROC is that if you get it from this, Z1, Z2 would be greater than 1. So, 1 by Z1 into 1 by Z2 should be less than 1. So, if you take Z, then this is Z1, Z2 would be greater than 1. So, the product of this is Z1 is Z2, it is greater than 1. So, it means Z1 greater than 1 by Z2 or Z2 greater than 1 by Z1. So, this is the equation of the ROC. So, which is the inversely proportional, Z1 and Z2 are inversely proportional. So, that is the curve which we get it here, and it is greater than Z2 is greater than 1 by Z1. So, this is the portion, the curve, and above which are the ROC of this case. The example which we had taken the sequence which is having the diagonal impulse only at the from N1 varying from 0 to infinity. So, this is not a straight line over here, that Z1, Z2, you can see the curve support. So, like in the previous examples where we have the lines and the portion of first quadrant, second quadrant, third and fourth quadrant. So, whereas this case is like diagonal ones, either it is going to be a step sequence with this diagonal, or the impulse with the diagonal ones are having this wedge support. It is called that wedge. There is a different support in the ROC case. The region of convergence will be different in these cases. So, we take another example in which that you can see the third quadrant one. So, A for N1, B for N2, this signal is known. We have done it in the two examples, and this is the one which is U of minus N1 and minus N2. So, U of minus N1 and minus N2, if we plot it, So if you take this sequence, this is going to be n1 and n2 depends on that. N1 0 0, it is going to be 1, and here it is a square, and for positive values of n1 and n2, it is ab and a square b square and so on. So for the negative values of ab, because this u of n minus n1 comma n2 can take negative values, so that it would result in here, this is a inverse, and here is a power minus 2, so a inverse and a inverse b inverse, and then b inverse here, b minus 2, b power minus 2 here, which is multiplied with a power minus 1 and so on. So the u of minus n1 minus n2 is the third quadrant step sequence. So like u of n1 comma n2, which is the first quadrant sequence, so this is a third quadrant sequence. So multiplying this two, so this region is becoming 0, this is becoming 0, and this is 0, and whereas this portion is now picked up in this product. So x of n1 comma n2 results in the sequence 1, a power minus 1 and minus 2, and b minus 1, and this is b minus 2, and a inverse is multiplied here also, and a minus 2 is multiplied in this sequences. So this is also a third quadrant sequence. Now we'll see the summation of the Z transform results in what is the resultant here. So n1 varying from now, this is minus infinity to 0, and n2 minus infinity to 0. So the summation can be limited only after drawing the sequence. Here we can, as though the sequence is given in this. So it is better first to plot the two, if you have the multiple sequences here, plot them and get the resultant sequence plotted, and we can decide the summations, like, because the Z transform summation spreads from minus infinity to plus infinity for all n1 and n2 values, and this restriction comes from the signal existence. So that's the points of which is in the first quadrant, second quadrant, or what is the value of in which. So here, after plotting this x of n1 n2, we could clearly see that the sequence is from minus infinity to 0 and minus infinity to 0 in n1 and n2. So the summation now results in minus infinity to 0, minus infinity to 0. So this needs to be changed to plus 0 to infinity to get the closed form solution. So when we change this from 0 to infinity and 0 to infinity, this becomes n1 is minus, and here it is becoming plus. This is what is becoming plus and minus over here, and similarly this is becoming minus and plus. So A inverse Z1 power n1, B inverse Z2 power n2. So this is the summation, it's separated summation from this. Now for the closed form, A inverse Z1 should be less than 1. Here similarly B inverse Z2 should be less than 1. Okay. So we get 1 by 1 minus is A inverse Z1, and similarly here this sequence. So from this OC, if we take, that is A inverse Z1 would result in less than A, and Z2 also will result in less than A from this two equations. So now the ROC of Z1A is this line and Z2B is this line. So now Z1A is the common area of this region, and Z2 less than B is this region. So the intersection region is OC here, which we had mentioned in the diagram. So for the third quadrant sequence, you can see the first quadrant was region of support was here, second one was here, the third one has the region of convergence here is this region. You can clearly visualize that through this diagrams. Now coming to the inverse Z transform, that is the case we had seen all the some of the examples of getting the Z transform. And if it is separable, it's very easy to get this Z transform using the 1D Z transform. Now how do we get the sequence from the 2D Z transform? So inverse Z transform, if we take is, it is obtained from this x of Z1 comma Z2, the sequence is obtained, and from its ROC. So ROC needs to be specified, as we emphasized in the previous lectures also, with the Z transform need to specify the ROC. So if ROC is not specified, and what are the chances of x of n1 comma n2, are the sequences, I will see through this example. And so 2D inverse Z transform is defined by the Cauchy's integral 1 by 2 pi j square C1 and C2. X of Z1, Z2 is the Z transform, and to get back the sequence Z power n1 minus 1 and Z2 n2 minus 1 integrating to dz1 z1. These two are the contour integrals. Here C1 and C2 are the closed contours. This is in the anti-clockwise direction, which is also lying inside the ROC. Okay, so that needs to be noted. And the contours C1 and C2 encircle the origin in the Z1 and Z2 plane. So Z1 Z2 plane, it encircles this origin. Okay, so this is the way to get the inverse Z transform. It is inverse Z transform, as we said, that it is not only depending on what is the Z transform is, it is also depending on its ROC. So some algebraic expressions of X of Z can represent two different sequences, same X of Z1 Z2, that we had seen through the example, but ROCs are different. Okay, so the case, it is not uniquely specified because of it, because one Z transform can have the multiple sequences, that is two sequences having the same Z transform, but ROC is different. So it's not uniquely specified. So if it needs to be uniquely specified, then we need to specify the ROC. That is what. So for a stable sequence, this unit surface is also included, as we had seen this in the properties of ROC. It includes the unit surface. The unit surface is Z1 equal to 1 and Z2 equal to 1. Here the magnitudes are, of course, these are magnitudes which we see in the ROC. So if we choose, suppose Z1 equal to e power j omega 1 and Z2 is e power j omega 2 in the contours which is 0 to 2 pi and 0 to 2 pi, where omega 1 and omega 2 are varying in this direction. So we can see the relation between the Fourier transform. So it is an inverse Fourier transform. So that's why we said that it is going to be the generalized version of the Fourier transform, where we had already seen. So the inverse Fourier transform, now if we reduce it, it reduces to the inverse Fourier transform. So similarly, the forward Z transform as well. So getting the Z transform and putting that Z is e power j omega, then it's a generalized version. So that holds true for the inverse Z transform as well. So it's a Fourier transform is a special case of the Z transform, or in the other way we can say the Z transform is a generalized version of this Fourier transform. That's also applicable or the true in the case of inverse Z transform. So now coming to the example of taking this inverse. So in taking a sequence X of n1 comma n2, so we can see that X of Z1 Z2 1 by 1 minus 1 by 2 Z1 Z2. What is the problem here is that there is no ROC specified in this example, and so we need to find this all possible combinations of X of n1 comma n2 for this Z transform. So what is the case of this? So can we write this first? We have to check whether it can be written in terms of the product of two X of Z's. So yes, it is possible there, because we have the clear cut sequences, the multiplication of two polynomials here. So x1 of z1 and x2 of z2. In that case, x1 and z1 and x2 of z2 is this first one here. This is 1 by 1 minus half and is equal to 1 power minus 1. 1 by 1 minus 2 is z2 power minus 1. Separating these two, so are this two, and so this is separable sequence. So we can get the inverse Z transform separately, x1 of n1 and x2 of n2. So what are the possible sequences and what are the possible ROCs for it? Okay. So for this case, if we take the first one, x1 of z1 1 minus 1 by 2 z1 minus 1, in that case first consider the case 1 in which z1 is greater than 1 by 2. So you can see here the sequence. So if it is z1 greater than 1 by 2, we will get 1 by 1 minus a. So from this one is less than 1 condition gives this closed form solution. That is possible to have z1 is greater than 1 by 2. Similarly, so in that case, first one, if it is greater than 1 by 2, the ROC, then the sequence was a power n u of n. So 1 by 2 power n1 u of n1. And if it is less than 1 by 2, so the second case is possible, z1 is less than 1 by 2, because ROC is not specified for z1 and z2. So if z1 is 1 by 2 greater than 1 by 2, we get the sequence, and if it is less than 1 by 2, then what the sequence is minus 1 by 2 or n1 u of minus n1 minus 1. So we had seen this sequence and this sequence resulting the same Z transform, but the ROCs were different. So we can conclude from that here is that thing. So there are two possibilities for this particular Z transform, only one case. So when this case Z1 greater than half or Z1 less than half. So for these two cases we get two sequences of x1 n1 and x1 n1 as well. So this is the sequence which is in the n1 varying from minus infinity to minus 1, and this is the sequence from 0 to infinity of n1. So these are the two possibilities in one case, that is x1 of z1, depends on the ROC. And if we apply the similar idea of this x2 z2 in the second part of the Z transform, 1 by 1 minus 2 z2 power minus 1, then z2 can be greater than 2, z2 can be less than 2. There are two cases again here. Z2 is greater than 2, in which it is going to be 2 power n2, that is here it is n2 u of n2, the inverse Z transform. So similarly, if z2 is less than 2, then we get this x2 n2 is minus 2 power n2 u of minus n2 minus 1. So this sequence is from minus infinity to minus 1. So there are two possibilities again. So if we take the first sequence has two possibilities and second sequence has two possibilities, and if we combine all of this, so case 1 and case 1, case 1, case 2, case 2, case 1 and case 2, case 2. So there are four possible combination of x1 and x1 and x2, n1 and n2. So if we take these two possible ROCs, we get four possible 2D sequences. So those are for ROC Z1 greater than 1 by 2 and Z2 greater than 2. So if we take both of them are in the case of greater than, that is first quadrant maybe, then it is going to be x of n1 comma n2 is this half power n1 and 2 power n2 u of n1 and u of n2. This is the first quadrant sequence. So the separable sequence, and we can write this as half power n1 into 2 power n2 u of n1 comma n2. So that's the possibility here. We can write it as half power n1 2 power n2 u of n1 comma n2. So this is one sequence. So if both ROCs are greater than, then second case we can take this is less than and this is still greater than that. So this would be the sequence which has 1 by 2 power minus n1 and u of minus n1 minus n1, and this is going to be 2 n2 and u of n2. So this can be again written as like 1 by 2 minus power n1 2 power n2 u of minus n1 minus 1 comma n2. You can write this. This is the second sequence we get from the ROC, and this is the second quadrant sequence. Now the case of 3 where it is greater than and this is less than, Z2 is second sequence has this 2. So this would be having this greater than 1. So where minus sign corresponding to minus 2 here. Okay. So minus 2, 1 by 2 power n1 is this case, and u of n1 is coming from Z1 greater than 1 by 2, and if it is less than, so minus 2 power n2 and u of minus n2 minus 1. So this can be written like 1 by 2 power n1 2 power n2 and u of n1 comma minus n2 minus 1. So this is the next sequence, the third possible sequence from it, n1. And this is the fourth quadrant sequence. You can see that this is the n2 is negative where n1 is positive. So this is the fourth quadrant sequence. And then we can get the other case, the left out case is Z1 1 by 2 and Z2 also less than 2. So these two cases results in the case of 1 by 2 power n1, 2 n2, there will be minus sign over here and minus sign over here, which gives the positive u of minus n1 1 and u of minus n. So this can be written like 1 by 2 power n1 2 power n2 and u of minus n1 minus 1 comma minus n2 minus 1. So this is the next sequence which is resulting in a third quadrant sequence. So there are possible sequences in this example only. There are 4 possible combinations for different ROCs. So a sequence x of n1, but it can have the same Z transform. So unless until ROC is specified, it will lead to multiple sequences here. So this is one example of the inverse Z transform. So we had seen a few more examples of Z transform in this lecture, just to have this impulse and step responses if we multiply, and if we have the diagonal impulses, and how do we change the summation of the limits in the case of Z transform. So that would lead to the simplification, actually n1 varying from 0 to infinity. So instead of having this minus infinity to plus infinity, the summation results in and reducing it to that closed form solution. That's a few example. And what the 2D impulse has the Z transform all over the Z plane, Z1 and Z2 plane here, and this region of supports for the first quadrant, second quadrant, and third and fourth quadrant sequences. How this can be a curve also. The ROC is depending on the curve. Z1 is Z2, case 1 greater than 1. Multiplication of Z1 is Z2 is greater than 1. That case it is Z1 and Z2 are inversely proportional. So the ROC is different in that case. That's a wedge support, we can say. The other case of inverse Z transform, if we take, it is similar, the kind of extension of this 1D Z transform. Z transform is generalization of Fourier transform. Similarly, the inverse Z also is this generalized version. We can get the specific version of that also can be defined in between this is Fourier and Z transform. The case which is having specified ROC, then we can have the unique time domain sequence or the space X of n1, n2. So we have seen one example of inverse Z in which there are 4 possible combinations of a sequence for 2 different OCs having the 4 combinations. So it's possible for this. So it is very important to define the ROC for a given Z transform, so that the sequence can be uniquely represented or get back the time domain sequence, the 2D sequences. So this same thing is applicable in case of 1D as well. So, and moreover, the stable sequence of Z would include the ROC of unit surface Z1 equal to 1 and Z2 equal to 1. So with this, we have seen the cases of Z transform and its inverse Z, and how to use the separability concept in the Z transform, and this would help in the filter transfer function. Again, as I repeat here, we would see the linear constant coefficient representation of the systems and its responses. How do we obtain them? We'll look at it in the next lecture. Thank you.